I take it where everyone can see the screen now. Ultra sensitive dynamic piezo sensors that improve technology. As Paul had mentioned, the title is slightly different. I'll get into that. Piezoelectric sensors naturally have a broad bandwidth. That's one of the attributes that's positive. But hello everyone. It's my pleasure to be here with you today, and thank you for taking time out of your busy schedules to attend. We are excited to provide the following insight on ultra-sensitive dynamic sensors and share how they can improve the semiconductor manufacturing. Prior to diving into our presentation, I would like to briefly introduce myself. Okay, there we go. Okay, shortly after graduating New York University some 37 years ago with a Bachelor of Science in Mechanical Engineering, I joined Kistler. From that time in the 80s up to the present time, my numerous responsibilities have centered around helping our customers in advancing their capabilities with our advanced technology. I'm happily married. My wife and I have two sons. Both are presently out of the house, my youngest being a student at Michigan State University. I'm active in the LinkedIn platform and can be reached as highlighted here. With me today is my colleague from Switzerland, Robert, who will also provide us with an introduction and some words on the Kistler Group. We will then move forward with our presentation.
Yeah, thanks, Jim, for introducing myself. And welcome to everybody on the call today. My name is Robert Hillinger, and as Jim mentioned, I live with my family in Switzerland, and I work at Kistler headquarters since 2018. And previously, I worked within the industrial automation industry. And today, I'm happy to support customers within the semiconductor industry globally to help to integrate measurement technology to make machines faster, increase performance, and help to increase yield. But with that, we will go in more details in a minute. Before, I would like to briefly introduce Kistler. We are a measurement company, so we are around since 60 years. Our claim is measure, analyze, and innovate, and that pretty much summarize what we do: measure, evaluate, draw conclusion, and then use the gained knowledge to improve processes and come up with new ideas which lead to innovations. Our core competencies is measurement technology. It delivers precise and reliable results, and even under extreme conditions. So we prepare and evaluate measurement results in such a way that our customers can draw then the right conclusions from them and optimize their processes. And our aim is always to help increase quality, to help to find new ways to innovate in order to be successful, be more productive, efficient, and so on. How we are doing this? So we are a global company with 2,050 employees worldwide, headquartered in Switzerland, but a strong presence throughout the world. Especially, I would like to highlight our production facilities, which are in Switzerland, in Germany, and in the US, where we produce acceleration sensors. And then you here can see some circles in Japan and in China, where we have technical support centers. But in addition to that, we have 60 locations globally where we support customers locally. You can see here as well a lot of patents and research and development. So we work closely with universities and research institutes, We have more than 800 patents, and our number of employees working in R&D is 300 plus, and investments are going from our turnover 9%, and we have, as I mentioned, globally 10,500 customers. And with that, I would like to hand over to Jim to move on with the presentation from the day.
Thank you, Robert. Now back to the presentation. Within this presentation, we have allotted time at the end to address open questions. I would also encourage everyone to use the question box. Please do not use the chat box for open questions during this presentation, as it will not be monitored. I would also like to point out in this presentation will be available afterwards. At this time, I would also like to get out of the way. Within this presentation, I will share information from several third-party sources. When the information is being shared, I will display that on the slide. This will allow you to verify or gain additional information. We will start off with the why. Why dynamic measurements are important. Then we'll address the what. What is a dynamic sensor, a broadband sensor, and provide brief overview on the transduction element. Here we'll review some of the key aspects at the front end of the sensor's production that ensures delivery of leading edge performance with ultra high sensitivity and bandwidth. Then we'll dive into the main portion of today's presentation, the how. Most of the time today will be devoted to sharing examples and solutions of semiconductor processes. Chip test as well as process monitoring control are widely done via the utilization of target-based optical and motion-based position sensing technologies. I would like to point out that the mechanical stress generated within the process is not detectable with these conventional measuring methods, yet it's equally important. Here we have an example on the right side of the screen. A known good die is attached to a known good substrate. While each component appeared to be in good tolerances prior to bonding, during the assembly phase, an actual crack developed as shown in the die. Force deviations occurring during the assembly process can lead to quality issues. In the next 35 to 40 minutes, I'll elaborate more on this. But first, let's examine what's under the hood of a dynamic force sensor. Dynamic force sensors utilize piezoelectric crystals. A unique property of piezoelectric crystals is that when they're mechanically loaded with force, as shown in the upper portion of the slide, the created stress causes an atomic level displacement, which in turn generates an electric charge on the upper and lower surfaces of the crystal. This signal output, it's in picocoulombs, is directly proportional to the applied force. On the lower portion of the slide, we illustrate various cuts that we utilize from the crystal. The compression sensing washers are shown in peach color. The shear sensing washers are shown in yellow color. Both of these crystals are used in the construction of a multi-component force sensor, multi-component X, Y, and Z. That's shown on the lower right. I would also like to point out that these crystals are directly stacked. Okay, I just advanced. Let's go back. Okay, these crystals are directly stacked, okay? And the electrodes actually collect the charges, sum them, and output them from the sensor. As the sensor's deformation of these crystals is extremely low, the sensor's output is very linear. This high linearity extends across the sensor's measuring range, which is of several magnitudes. See, 10 kilonewtons, 100 kilonewtons, 100,000 kilonewtons. Let's look more at this amazing crystal. When building sensors, our innovation starts with this piezoelectric transduction element. I would like to point out the rigid piezoelectric crystal the rigid piezo crystal directly acts as the sensor's transduction element, converting the mechanical applied energy into a proportional electrical signal output. Under the hood of each piezoelectric sensor, the crystal could be quartz or one of our other piezoelectric crystals. We call them piezostar. That's where you see the different colors here. Let's get the laser pointer. The green or the amber or the white. So we're using more than one crystal in our sensors. That's how we're actually tailoring the performance of the sensor, either the sensitivity or thermal performance, to our customers' needs. On the far right of this illustration, we provide a glimpse of our in-house ability to precisely machine each sensor's crystal, thus ensuring the overall sensor's performance to our customers' needs. In this demonstration, an O-ring is placed on a piezoelectric sensor, featuring a measuring range of 10 kilonewtons. That's about 1 ton of force. The measuring result is shown on the graph on the right. This graph successfully illustrates that very low force changes within a fraction of a gram are easily detected and with very high resolution. The unique capability of the dynamic sensors is that they enable one to view small force deviations that are not visible nor possible with another force measurement technology. Let's say a former strain gauge based sensor being utilized in such a demanding application. The takeaways on dynamic force sensing can be summarized as starting with the high rigidity due to the transduction element and its atomic level displacement. This results in a very high linearity and a wide useful measuring range or bandwidth. Given the lack of movement, the sensing system benefits with a very long lifespan, very high resolution, and repeatability. Dynamic piezoelectric sensors provide very compact footprint size, especially when compared to other sensing devices. Now, regarding the market, I would like to point out that the market demand for ultra-thin wafers continues. And chip utilization within thin products such as ID chips for credit cards or small size chips for AirPods for music. Furthermore, given the latest advancements in extending Moore's law and the evolution of advanced 3D chip packaging and heterogeneous integration of chiplets, wafer thicknesses are required to be at least 5 microns. As shown here, that's smaller than a human hair, white and red blood cells, and even bacteria. Furthermore, I'd like to point out that as the wafer thickness decreases, so does the individual die strength and die warpage increases. With this in mind, I will share how piezoelectric force is improving semiconductor processes by sensing the stress generated at the tooling and with the utilization of a dynamic force sensor that provides higher resolution and allows for additional process insight at the physical interface to the wafer and the die. I will cover machining of thin wafers, producing of thin dies, handling of thin dies, assembly of thin dies, and of course, because some semiconductor industry loves to test, we'll address the testing phase as well. We'll start out with a front-end process involving wafer manufacturing, more specifically, the process of CMP polishing and the needs for improving press force accuracy. In the CMP process, I would like to point out that 2 force vectors, as shown here as red arrows, forces required within this process. One force for the wafer's polishing action to the pad, and the other force for conditioning the pad surface. Within the patent shown on the right, Lam Research recognized the need to improve downforce accuracy within CMP and wafer polishing. Simply put, they stated the present systems based solely on pressure have their accuracy adversely affected, and this is primarily due to friction losses associated with the pressure sensing approach. This patent also provides us a great lesson that when selecting a load cell, one must consider the force sensor's resolution capability. Beyond just selecting the required measurement range, the need for resolution enables one to sense the smaller occurring forces, let's say at a wafer interface. Kistler dynamic force sensors provide improved measurement resolution, enabling one to sense the wafer to pad interface. I would like to share the force sensor utilized in this patent only had a fixed range of 500 pounds. The sensing technology within the sensor lacked scalability, and with it, the ability to measure fine resolution. The force sensor had 0.1% accuracy, but it was locked in at 500 pounds. Hence, the resulting resolution was a half a pound and unable to detect the fine pad to wafer interface aspects occurring in the process. As stated early, semicon chips are becoming thinner, and with it, the precision within the process regarding wafer flatness remains very important for individual chip performance, as well as demands for improved process feedback for better process insight and traceability tied to each wafer. Let's say the end customers in the automotive market. Dynamic load cell sensors are installed within these processes, within the base fixture, at the flange structure supporting the turntable, yet also in the spindle head. This is especially for assembly bonding applications to be discussed later. These dynamic sensors provide indication of the initial wafer contact, the actual downforce pressing on the wafer, and live feedback for monitoring and control. Higher performance machines, individual force sensor outputs provide the means for live feedback, which enables the spindle head tooling to adjust within the process. Your benefits, higher precision and documentation. Now let's talk about another wafer process, specifically dicing and lamination, and the needs for die tension during the lamination process. Here we're looking at the traditional wafer dicing process whereby wafers are first thinned by grinding and then cut into dies. The challenge is that as the workpiece gets thinner, dicing increases the likelihood of chipping. Hence, with ultra-thin wafers, there's an increased concern for breakage. So let's examine another approach for the dicing process. In dicing before grinding, I will only focus on the first three steps. The first step, in the red box, the wafer is half cut or slotted. This is where the dicing is performed. In the second step, shown as yellow film, back grinding lamination placed over the wafer. This protects the wafer's printed circuit board. In the third step, shown as a blue box, the wafer is flipped and the back grinding occurs from above. In this step, the wafer is thinned. Each die separates from one another, then only being held in position by the back grinding lamination tape. In the next slide, we will examine how the earlier process of lamination influences a later process result with the individual dies. On the left, the wafer is represented and each die is equally spaced after back grinding. This is the desired die alignment result. On the right side, the tension in the back grinding tape is released, causing the dies to be misaligned after the back grinding process. This root cause, as noted, an improper lamination tape process. Here's an example of a retrofit solution, whereby the measurement solution has 4 tubular pin-looking sensors installed in the lower machine support. This is the instrumented lower structure that supports the darker round wafer contact area. In the upper right, the individual sensor locations are highlighted by 4 red arrows. As these sensors are highly rigid, once they're installed within the mounting board and preload, each sensor can sense a very low force, even the measurement of the structure's internal strain. In addition to the sensor's superior resolution capability, this measurement system provides an output in real time. This is a desired feature necessary for sensing uneven loading conditions and for control feedback during the film application process. I would like to mention what gives this sensing system a superior performance. Begins with the sensor's unique internal proprietary sensing crystal. The measurement system offers very fine resolution and a high useful output signal. For example, 13 thousandths of a microstrain can equal 1 volt output. Now let's discuss a back-end assembly process, specifically processes involving pick and place, die sorting, and chip removal, and the needs for die stress control and the determination of proper peeling energy during the chip removal process. Here shown, where we show a thinner die is indeed more flexible. Please see the upper right portion of the slide. I'd like to point out that the gray colored chip bends as it's forced to release from the blue colored membrane, and the membrane's adhesive is detailed in orange. For process reliability, several injector needles may also be utilized. The injector needle structure provides an excellent means for tooling process feedback, for determining proper die peeling energy, and in sensing the process to avoid die cracking. Dynamic force monitoring provides a means for detecting die cracking stress and proper peeling energy. In the next slide, I'll go more into detail on this. We know from physics, energy is a measurement of the ability of something to do work. Work is defined as force times distance, let's say in moving a block a certain distance up a ramp. In this solution, the dynamic force sensor is installed within the ejector pin's pin mechanism. This directly measures the effort to remove or peel the die from its membrane. The pin movement is tracked. On the left side, we view a curve that has pin position or distance plotted on the lower x-axis, and pin force, which is the effort encountered on the pin during its movement, plotted on the y-axis. The work performed in removing the chip from the membrane is the integral of this curve, or more simply stated as the area under the curve. The process monitors utilized to track both these parameters and provide a detailed signature of the process. A pass-fail toolbox included within these monitors provides for waveform evaluation as well as reporting traceability tied to each die removal. Now let's take a deeper dive into assembly, specifically thermal compression bonding and the needs for proper wetting of bump pads. In thermal compression bonding, one must control three parameters. They are temperature, z-axis or vertical movement, and assuring proper bond force is ultimately achieved. On the next slide, we'll take a closer look at the control aspects of these three process parameters. Sorry for the lack of resolution on the graph. The chart, on the chart, the blue curve is the bond force. The gray curve is the bond head's vertical position, and the red curve is the bond head temperature. Now I will step through the control steps for these three processes. The bond head position moves down, that's the gray. The force sensor senses that stack up has been reached, so it's building up, and now you just made contact right here, okay? Then the temperature ramps up. So once you've made contact, the temperature ramps up. Sorry, oops. Sorry about that. Okay, then the temperature ramps up. As the temperature ramps up, the solder starts to flow, the force drops. At this point, the bond head blindly moves forward until the force rises. So that we've just sensed that we've made contact with the molten solder, and the position stops. Temperature is still held, so it's going to that locks in the position right here. That's assuring that the solder wetting of the bump pads occurs. At that point, the bond head retracts to assure proper final height spec. The force signal drops, and the last step, the temperature drops, locking in that position. Okay. So that's step one. I just wanted to show you how those three process parameters dance or work together. I'd also like to point out that these two trigger points, shown in green, show that dynamic force provides feedback for position control, confirming that the actual physical contact has been made. And the resolution capability of the dynamic force sensor is very important, and also within assembly processes in the semiconductor marketplace. Here we illustrate the tooling head and provide insight on the three dynamic force sensors. That three dynamic force sensors are utilized, not just one, but three. The three separate force signals are required to allow for measurement of warpage, an indication of desired parallelism. We also summarize the advantages of the dynamic force sensor measurement system: high resolution, greater than 0.1 grams. I would also mention good repeatability and compactness, as well as providing real-time closed-loop control. The block diagram also illustrates directional flow and feedback of the main components. In summary, the benefits of dynamic force monitoring are as shown to the right. Contact parallelism, if this is occurring or if it's desired parallelism. Increased speed and performance, because these are highly rigid sensors. You're not adding rubber or something compliant in the system. And the highly rigid sensors allows for bonding of the thinnest, most brittle components with improved accuracy. Okay. Given there's a lot of testing performed within the semiconductor ecosystem, I believe it's appropriate we close out our presentation with some discussion on electrical testing, specifically process testing involving micro bumps and spring probes, and the needs for verification of functionality and in support of traceability. A certain in testing is to perform the test without damaging the device under test or altering its performance. In this illustration, we have an electric test being performed on a single micro bump, say of a flip chip circuit. On the left portion of the slide, probe head is shown contacting the individual bump for electrical test. And the result of this testing right here is that the tester says it passes. Everything's good. However, we see on the right side, after this electrical test, the bump pad surface is mechanically damaged and a divot results. If this is not caught right away, the chip or batch of chips will later be discovered defective during in-service operation. In probe testing, it is desired that the micro bumps are not hit with too much force, as this will lead to mechanical and electrical reliability issues. In this illustration, we're showing the tooling. The tooling actually directly measures force and displacement. That's the force sensor right there. From physics, we know, or more specifically from Hooke's law, we know that if an object applies a force to a spring, then the spring pushes back with an equal and opposite force onto the object. Hence, the force a spring probe exerts on an object, or in this case, the micro bump, is simply stated as F equals minus Kx. In the below graph, we plot the force from the spring per the displacement of the spring, or the distance traveled. The slope of this force versus distance curve is the spring constant K. On the next slide, we'll look at the actual end-of-line testing performed during machining of spring probes. A Kistler dynamic sensor is shown here as the blue arrow. It's a sensor, it's hidden behind this L bracket. It measures the spring force of every spring probe manufactured. In this test checks the spring loaded probe prior to the final assembly and arrays and shipment to customers. By integrating quality control into the automated manufacturing process, bad parts are directly removed from production and the product traceability is maintained. It is well known that testing multiple chips on a wafer requires probe cards to be utilized. Again, the concern is not to damage the individual die contact points during the wafer testing. Here, manufacturers of wafer probe cards must also verify that ultra-low probe force is generated even when the probe cards are operated at over-travel conditions. I am now approaching the end of this presentation and will wrap up the key points on the next slide. So in summary, chemical mechanical planarization, CMP, we can improve the press force accuracy. Wafer lamination, die tension control. Die sorting, die stress control and peeling energy. Thermal compression bonding, initial contact and feedback for the wetting bump pads. Testing phase, contact force on the micro bump pads. Dynamic force is a critical process value in the semiconductor production. With this slide, our presentation has ended. At this point, we will open up the presentation for replies to questions.
Thank you, Jim. So, let's see, I'm looking at the questions. Okay, the first question is a general question. Will the presentation material be sent to us later? And the answer is yes. You'll get an email. Thank you for attending the webinar, and we will have the slides in that. all the slides shown today. Okay, I have a question. You talk about your sensors, but can you talk more about what is the material? Did you mention that?
Well, yeah, I showed that picture of several crystals. You know, one was green, one was amber, one was clear. The clear crystal is quartz, okay? We're using quartz. It's actually man-made quartz. It's not the stuff you get out of a cave because it just has inclusions like you're looking for the perfect diamond and you get a diamond, same thing. We're looking for the perfect quartz. It has to be instrumentation grade quartz. So the quartzes are actually grown in autoclaves, so they're pure, okay? So that's quartz, but then again, the benefit Kistler provides, we've been in business over 50 years, is we know how to machine it precisely. And that's where we get the additional cuts. There were 4 cuts there, I only talked about 2 of them. That's one material. The amber and the green one is a Ki 85, the other one's a Ki 100 crystal. Ki is Kistler Instrument. It's a proprietary crystal that we grow. We grow it, so it's proprietary. I can't talk more about it, but it's grown for certain features that we deliver in the product, which I've been talking about here in this presentation. So yeah, there's more than one crystal. One is everybody knows about quartz, but the other 2 are Kistler proprietary crystals.
Okay. So the ones that are proprietary have been basically designed to have certain capability to
Correct.
aid in the process. Okay.
Correct. The capability is resolution. That's one capability. The other capability, because these crystals are used in high temperature flame rocket type applications, temperature. So our sensors are used all over the world in a number of applications. We understand the issues and the processes, so we developed the crystals to address that.
So okay, here's another question. What is the minimum frequency of the dynamic force this sensor can respond to, and with what accuracy?
Yeah, the minimum part of that is the crystal needs a signal conditioner to actually make the output useful. Okay, the conditioner has a bleed off of a capacitor, so the low end frequencies are typically about 0.5 hertz. But what we're finding in an assembly is you want to make the parts as fast as possible. You don't want to take, I mean, if you're taking a half a day a weight application, this would not be necessarily ideal for weighing something. But for assembly and in manufacturing, you want to make as much stuff as quick as possible. So the time duration is short, and these excel. Dynamic sensors excel. The other thing I wanted to point, did I answer? And it's very accurate because the deformation of the crystal is atomic. Nothing's wearing out. You're not measuring on a trampoline. You're measuring on a rock, is the analogy I use. Did I answer that question? It took a long.
Hopefully.
Okay.
Yeah, we do have a question.
If I didn't, please let us know. We can always do a sidebar later on. But what I'm trying to do is I'm trying to highlight how we're different. Because I often run across, yeah, we tried a load cell and there it didn't work. Okay, why didn't it work? Let's talk about it. Okay.
Yeah, there is a request for your email. Do you have that?
Yes, I do. It's jim.macy, M-A-C-Y's last name, at kistler.com. That's my email. First name dot last name at kistler.com. Kistler.
Okay, jim.macy at kistler.com. Does james.macy also work?
I think it does. That's my legal, that's on my passport. Nowadays during travel, I have to use that. I think they both work, james.macy and jim.macy. I think they both work. That's my understanding.
Okay, so what is the piezoelectric? So there's a statement and a question. The questioner says, I know the piezoelectric measurements are not for static measurements. Is that true? I don't actually.
Yes.
Can you comment on that?
Yes, I can. They're not for measuring long-term static measurements. That's why I said weight, like a weight application. That's where the red light goes off, that we have to observe caution. That's where when you speak with the application engineers, they can properly guide you on that. But we can measure quasi-static, which is short-term static. Okay, short-term, there's a clock going. The racer's clock. What's the process event cycle duration? That's usually what we want to look at, is what's the cycle duration that makes it static. If it's hours, forget it. If it's a minute, possibly. And the reason I say possibly is if we're generating enough signal, that bleed off or that drift that we're talking about from the amplifier, it's a fixed rate. It's just drops coming out of a bucket. But if I have a full bucket of water, what's a few drops? That's what we're playing off to see if, it's the Achilles heel of this technology, but often in manufacturing, it's not an issue.
So you have okay, wait, here's another question. Do you observe process yield improvements for the application of thermal compression bonding when you use your sensors?
Yes, I mean, Robert, if you want to address that from the Asian market side.
Sure, that's the case, and that's also why customers are using our sensors, because they not just monitor the force, so they really control it and use it to control servo motors within thermocompression bonding, and this gives them a higher accuracy, and that leads to higher yield. So that's the case, yeah.
Yeah, so that was one of your applications. So your observation is when companies put these sensors in their processes, is it a general statement that you see yield improvement for all your processes?
Yield improvement, because they have insight into the process they didn't have before they used our sensors. Yield, and then also traceability.
And is it difficult to integrate your sensors into an existing tool?
We prefer to deal with the machine builders while they're designing the tooling. That's the best position. But as I showed you in the lamination process, because to put the sensor in, you have to cut metal and you have to integrate the sensor, what makes it challenging. So it's better to have our discussion at the offset when the page is still white. We all get together and we discuss the best approach. However, with that said, there are options we offer for retrofit, as I demonstrated in that lamination process, where instead of cutting the metal, you drill a hole and then you preload the sensor in the hole, and now you're measuring the strain in the structure. But our preferred way is a direct force with the load cell installed. So there's no one magic answer here. The best approach is that we consult it at the offset, or when you'd like to implement this, we can have a discussion.
Yeah, understood. Do we have any more questions? Well, I want to thank you guys for introducing us to this technology. And it's interesting. You guys have these proprietary materials that have been developed specifically for these processes, and they appear to improve the yield and performance of the equipment making these processes and the process yield also. So very impressive.